So today's the next webinar in the series of building blocks that 475 is doing each month. Each month is a different topic. And this month we're talking through the IECC climate zones and how to be adjusting your wall or roof assembly based on the climate zone. My name is Nick Shaw. I'm with 475 High Performance Building Supply. This presentation is going to kind of give an overview of the climate zones and then go into how your water and air and vapor control and thermal control strategies might slightly differ based on which climate zone your project is in. So as I'm looking at wall and roof assemblies, there's this order of priority. Water control being number one, that's why we went into caves to begin with. Then we're thinking about air tightness. A lot of projects have the option to have an exterior air barrier at their water resistant barrier, their house wrap, and or an interior air barrier that's normally doubling as their vapor control layer, a vapor variable membrane. Ideally, projects have both, but we'll kind of talk through some climate zone specific considerations. Similarly, with vapor control, we're oftentimes having our interior air barrier double as that vapor control layer using vapor variable membranes or humidity dependent vapor retarders, the Intello membrane, whether that's the Intello Plus or the Intello X membrane. And then we'll also be kind of talking about the exterior vapor permeability that's ideal for your house wrap or sheathing based on your climate zone. And then lastly, we'll be discussing your thermal control, your R value, what type of insulation you're using, and where it's placed within the wall assembly. So jumping into it, the IECC, International Energy Conservation Code, have these different climate zones. The lower the numbers, the more warm the climate is, the higher the numbers, the more cold it is. So we have a temperature change, based on those numbers, based on what climate zone you're in. But then there's also your region based on your moisture, i.e. how much exterior precipitation is occurring. So, in kind of east of the Rockies, you're in a moist climate, i.e. a humid climate. More in the Rockies and west, you're then in a dry climate or a marine climate when we're more directly against that west coast of the Pacific Ocean. We see a similar thing in Canada. Sorry that I'm not showing the Canada IECC climate zone map, but that is available online. And it is kind of what you expect that most of Canada is in climate zone 7 or 8. There is a sliver in 6 and a marine area around Vancouver as well. So looking at that moisture regime, so that A being moist, B being dry, C being marine, this is just directly based on how much precipitation happens during the year. So moist meaning more than 20 inches of annual precipitation, whether that's rain or snow, dry being less than 20 inch. And marine is kind of an interesting category because you're having a drier summer and a wetter winter. So you're having most of your precipitation during the winter, maybe while it's snowing, and you tend to have a drier summer season. So that's the distinguishing between marine and the others. You can be on the coast, on the East Coast, and you're still in a humid or moist climate because you're getting a lot of precipitation, even though you're next to the ocean. You're still in a moist or humid climate when you're on the East Coast. Looking at the thermal side of things, so we classify this based on your heating degree days or your cooling degree days. How much of the year are you having to heat your home, i.e. it is winter outside, or how much of your year you need to have air conditioning cooling your home, i.e. summer outside. So climate zones 1 through 3, those are cooling dominated climates, i.e. it's hot out, and you are running an AC for most of the year. Climate zones 5 and up, it is a heating dominated climate, i.e. it's cold out, yet more intense winters than summers. And then climate zone 4 is kind of in the middle spot. And we're seeing those being a little bit more even in terms of heating degree days or cooling degree days. They are in general tending to be more heating dominated still, that winters tend to be a little bit more intense than summers. But we'll kind of be seeing how climate change is adjusting that. But yeah, so the overview is you have moist or humid regions in A, dry or arid regions in B, and then marine in C, and then the lower numbers meaning warmer climates, the higher numbers meaning colder climates. And then there's the Building America program that's doing a lot of this research and figuring this out, and they just have a different names for this. So instead of saying for A, i.e., mixed humid region, they are calling it mixed humid, and they're not necessarily using those numbers and letters, but they're all really getting at the same principles, and it's really really rooted in is it really humid outside or is it dry outside? And are you mainly having more intense winters or are you having more intense summers? So that's just kind of an overview of these climate zones. There's a lot of more research and getting into what specific amount of heating degree days and things like that that you can read about in the IECC documentation. And some of these regions do have small little microclimates, or your site specific spot might have a little microclimate. But these are really helpful guiding principles for when we're designing our wall and roof assemblies, typically our above grade walls. So back to that order of importance of shedding the water, that is really number one. That is regardless of your climate zone. You want to keep the building dry if it's humid out or if it's dry out. We want to shed the water away from the building. This can be fairly simple, just shiplap or overlap the seams. Here we're showing a monopoly framed building where the wall roof sheathing is connected right to the roof sheathing. And there's no big eave or overhang at this stage of framing. Oftentimes they're doing like an applied rafter tail system to create that overhang down the line. But this just eases and makes a really simple transition from your waterproofing on the roof to your waterproofing on the wall. And technology has gotten better for these water resistant barriers, these WRBs. The newer technology coming from Pro Clima through 475 is monolithic and utilizes a TEEE film, this film within the membrane. There's a functional part within the exterior membranes from 475. And that functional part is incredibly airtight, incredibly watertight, and quite vapor open, vapor permeable at about 38 perms. And this requires active diffusion, active transport along a molecular chain to transport that water molecule and keep that vapor and create that vapor permeability. While older technology, Tyvek, Typar, Henry Blueskin, these types of materials that are microporous, where they're taking oftentimes like a sheet of plastic and stretching it very taut, so there's little tiny holes or little tiny pores within that membrane. There's a reason why you can't use that same membrane for the wall and the roof. It's not as watertight as what you would need for a roof application. So they tend to clog or deteriorate over time, and we're not as robustly watertight or having that durability of the monolithic membranes. These microporous membranes, the wood tannins of the siding or the framing can break down those pores. So we have a lot of like durability and longevity issues with this older type of technology, but they can still be quite vapor open or vapor permeable, which is a good thing for most of our climates. So the exterior membranes coming from 475, there's the Solitex Mento series. These are membranes that you staple, install, and then tape the seams. They're mechanically fastened. And this membrane is incredibly robust. The difference between the 1,000 or 3,000 or 5,000 is just the level of protective fleece that's on that membrane. And that protective fleece helps it withstand longer UV exposure or more durable in terms of boots walking on it, but still has that TEEE film within it. And then the other series of exterior membranes that 475 offers is the Solitex Adhero 1000 or 3000. And that's that same TEEE film with a protective fleece outboard of it, but now we're applying an adhesive to the interior side. This adhesive lowers the vapor permeability some. We're getting more about a perm rating of 12 for the Adhero 1000 or more like an 8 for the Adhero 3000. So it's that adhesive that is dropping that vapor permeability. It still has that TEEE monolithic film within the membrane. And then the main difference between the Adhero 1000 and 3000 is, again, that exterior protective fleece. So the 1000, that fleece is less robust, lower UV exposure. You probably don't want to walk on it as much. So we're only using it on walls, while the 3000 is a more robust fleece, longer UV exposure, more comfortable walking on the Adhero 3000. So this is what we're waterproofing and air sealing on the exterior sides of the sheathing with. This house wrap, this water resistant barrier from 475. So now we're looking at the air tightness. We've shedded the water. That was the main concern. We want to keep the water out. Now we're looking at how to make the building airtight. And we're oftentimes locating where what we call the primary air barrier is, depending on the climate zone. I don't really like the term primary air barrier because it kind of means that the secondary air barrier you don't need to worry about. I am fine with as many air barriers within an assembly as possible. Air tightness and having redundancy in air tightness is only helpful. The concern would be is if some of those materials were vapor retarders or vapor barriers. We don't want to have two vapor barriers in the assembly. That's creating a vapor sandwich where we could trap the moisture in between. But we're comfortable having as many air barriers as we'd like. And oftentimes the exterior air barrier is vapor permeable and the interior one is vapor variable. That arrangement is really helpful in more northern climates, climate zones 5 and up, where we're mainly drying outwards and we can utilize that interior air barrier as our vapor control layer, i.e. the Intello membrane that's vapor variable. But in more humid climates where it's always humid outside and it's very moist and wet outside, we want to stop a lot of that air transported wetting from the outside coming in. So we tend to want to have a class 3 vapor retarder on the exterior, but we want to air seal just to stop that air transported wetting coming in. So we shedded the water. Now we're looking at how to make it airtight. And a big key thing for keeping the risk down is just preventing warm air from meeting a cold surface. This is the main risk in a lot of these assemblies. This occurs, here we're seeing a window, the glazing, maybe it's a single pane window, so we're not having that warm interior surface temperature. So that area, that surface temperature is cold, and our interior warm air is meeting it to condense. It's the same thing that's happening with your soda can out in a summer day. The can itself is cold, the warm outside air is meeting it. That warm air can hold a lot of moisture. The cold air at that surface of the can cannot. So when the warm air meets it, it creates condensation, since that warm air can hold more moisture than the cold air. So how this occurs in wall assemblies is when we don't have exterior insulation, that sheathing can be quite cold in our northern climates, climate zones 5 and up or 4 during our winters. And so what we're oftentimes trying to do is add enough exterior insulation to warm that sheathing to prevent this, where our warm air is moving through that cavity insulation to the bats and meeting the backside of that sheathing that is cold, where it could condense. This would all be flipped in our more humid or warmer climates, our climate zones 3 and below. Then we don't want our outside humid air moving through that insulation to meet our drywall that is being air conditioned where it's a colder surface. We don't want that warm air to meet it where it condense. Again, we're just preventing warm air from meeting a cold surface. So in northern climates, we're oftentimes including this interior air barrier. That is the Intello Plus or the Intello X membrane. So the key thing that it's doing is just keeping your warm air within that conditioned space and not letting it move through that insulation where it would meet the backside of the sheathing during the winter. Now, with this type of interior air sealing, we don't necessarily need exterior insulation. We don't care what temperature that sheathing is getting because we're keeping our warm air within the conditioned space and not letting it meet that sheathing that could be getting cold. So now we can do double stud construction and types of assemblies that are prioritizing a thick layer of fibrous, vapor permeable, oftentimes hygroscopic insulation within that cavity. We still want to be thermal bridge free, so exterior insulation can be helpful for that, but we can eliminate thermal bridges in other ways, such as double stud. So yeah, in general, we do want to ideally air seal both sides of that insulation. The exterior would act as your water resistant barrier. We want that to be about a class 3 vapor retarder for our humid climates, and then vapor open on the interior in our humid climates. And then in our more northern climates, I'm saying humid, my apologies, I mean warm, warm and humid. And then in our more northern climates, we want to be as vapor open on the exterior as possible. And then we're utilizing this vapor variable membrane on the interior. But just making it airtight on both sides will help prevent any thermal bypass. This is wind washing, where we get air convective loops moving within our insulation layer that can greatly reduce the R value. So our air tightness levels will affect our effective R value. When a manufacturer gives you that R value, it's from a lab where it was airtight on both sides of that insulation. We want to prevent any air transported wetting. Air is really wet. It's where most of our moisture is coming from. So if we stop that and make it airtight, then we're only adding moisture through diffusion, which is a lot less moisture. And by air sealing on both sides of that insulation, we're also accounting for our seasonal climate changes, that even if you're in climate zone 3, fairly warm, you still might have some cold spikes, some cold winters. We've been seeing these intense winters in Texas, for example, that is quite a warm climate. So it accounts for that and helps, keep things low risk. And we're in general not really placing a true vapor barrier. We need true vapor barriers below grade. The soil is always wet. That's why we have like a subslab poly membrane. And we would want a true vapor barrier on the top side of a flat roof because you could have water pooling or ponding. But otherwise, we tend to want to dry through diffusion in either direction. So I've been talking a lot about that vapor control because that vapor and air is really tied together. Air is really wet. And if we prioritize that air sealing, now we're only wetting from diffusion, but we're also only drying through diffusion. So in those more humid climates, we want an exterior class 3 vapor retarder, which is between 1 and 10 perms. And then in more northern climates, we want to really prioritize that vapor variable or smart vapor retarder, humidity dependent vapor retarder on the interior with the Intella membrane. So I've been talking about different vapor permeabilities. There's a classification for this. So the lower the number, the more restrictive or vapor retarding or vapor barrier it is. The higher the number, the more freely moisture can pass through. So wood, truly vapor open, a high vapor permeability, glass, vapor closed, a vapor permeability of 0. So there's a classification of vapor perm. Class 1 is 0.1 or less, 0.1 or less. So moisture is really not moving through that. That'd be like a true poly membrane. Then we have a class 2, which is 0.1 to 1. So we say class 2 vapor retarder or vapor semi-impermeable. So this is a very low permeability. Moisture can barely diffuse through, but it will really struggle and take some time. There's a lot of code around class 2 vapor retarders and roofs. So we see class 2 around code concerns oftentimes for roofs. Class 3 is between a 1 and 10 perm, so moisture can still pass through it, but it's a little bit restrictive. It's a little bit retarding. And this is kind of the sweet spot for like climate zone 3, that we want this on the exterior. It's a humid area, climate zone 3A. It's quite humid outside. We still need a dry through diffusion outwards during times in the winter, or even sometimes during nights, even in the summer. But that humidity, we don't want diffusing too much inward since it's always constantly a high humidity outside. So we find this class 3 is just about right. Then we have vapor open or vapor permeable anytime the number is greater than 10. So the Solitex Mento membranes are all vapor open. The Adhero 1000 is actually a vapor permeable 12. So it's vapor open, vapor permeable. There's a lot of materials that have different permeability based on a dry scenario versus a wet scenario. So they might have a lower permeability in the dry cup test and a higher permeability in the wet cup test. And a lot of materials change their vapor permeability based on that type of testing scenario of moisture. So we get some vapor variable materials. Plywood is vapor variable, pretty much everything wood or paper based is. And then there's this newer technology, i.e. the Intello membrane, that's a humidity dependent vapor retarder that's responding to the relative humidity around the membrane and going from a class 2 vapor retarder at 0.13 perms to truly vapor open at 13.2 perms. So this would be the red membrane located inboard of that insulation. This is the Intello Plus or the Intello X membrane. It is incredibly airtight. That's the first thing that we're doing to reduce that risk to prevent our warm air from meeting that cold surface during the winter. But we're further reducing the risk with this vapor variability. So in the winter, we have a low relative humidity. Again, cold air can't hold as much moisture, so it tends to be drier. So this responds to that low relative humidity and drops down to a class 2 vapor retarder. And then in higher relative humidities, once we're above around 70-ish RH, this membrane becomes quite vapor open at 13.2 perms. So it's never going to trap moisture. If there is a moisture buildup, if there's a high relative humidity buildup around this membrane, it will become vapor open. So because it will never trap moisture, it's why we're comfortable using it in more humid climates on the inside. Even when the vapor drive's coming from the outside in, we might very rarely want it to be a class 2 vapor retarder in these like climate zones 2A or 3A, but it won't do any harm. And in fact, just having that interior air barrier is quite helpful. So looking at this as a vapor curve, we have vapor permeability on the vertical, we have relative humidity on the horizontal. Mold tends to grow or accumulate about 80% RH. Anytime we're above 41 degrees Fahrenheit, below about 104, at about 80% RH, we tend to have some mold growth depending on the substrate. So this membrane is going from as vapor retarding to as vapor open at about that 70% RH. That's our risk threshold. We don't want to moisture load too much too early at a lower relative humidity, but we really don't want to trap any of that moisture. We wanted to allow it to dry inwards before we run the risk for mold growth. So through different WUFI analysis or other testing, we've kind of found that this Intello Plus or the Intello X membrane is really the sweet spot. And ideally, we want this on the interior side of the insulation, or at least most of our R value outboard of it. It can kind of be in the middle of the insulation, but we want the majority of the R value outboard of this Intello membrane. So here we're showing it being installed. It's lining the interior side of the insulation. It's a Passive House certified component. And as you start to really increase the levels of insulation, this interior air barrier and this smart vapor variability becomes really key. As you're drying more out during the winter, as your winters get more intense, this becomes more key. When you can't dry out in the winter, this becomes really key. Even in like a climate zone 3 or 4, if you're being vapor closed on the exterior, maybe that's because it's a flat roof and you have an EPDM or TPO membrane, or maybe you needed to use an exterior vapor barrier for some reason. Maybe that's like a foil-faced polyiso or an XPS exterior rigid foam. This Intello on the interior becomes really key. That vapor variability is key because when it wants to dry outwards, that vapor closed material on the exterior won't let it. So we don't want to moisture load our assembly more with our interior humidity at that time. It's really helpful when your insulation is not hygroscopic. Hygroscopic meaning insulation like a sponge that can kind of safely hold moisture. So hygroscopic insulation such as cellulose can kind of create this drying reserve and can safely hold that moisture. But if we can't safely hold that moisture, then this vapor variability becomes more key. And then when we have wetter construction, we really want this vapor variability so it can dry inwards and not trap any of that wet wood or plywood sheathing, or maybe it's poured concrete or something like that. So the interior air barrier is greatly reducing risk, but we're further reducing risk with the vapor variability of the Intello Plus or the Intello X membrane. This is an infrared camera shot, a thermal imaging shot. And on the left, we have our old style of construction where we didn't have any insulation and we just oversized our mechanicals. And this was very low risk because energy just passed freely through these walls. But now we're super insulating. We're limiting the amount of energy that passed through these walls. We're much more comfortable, much more energy efficient, but we're much higher risk. We need to think about how this assembly is going to dry through diffusion because we're not baking it dry anymore. So it needs to dry through diffusion or it won't. So in the summer, we need to allow that assembly to dry inwards. And in the winter, we need it to allow it to dry outwards. And we can kind of see this also as our climate zones. So when we're in climate zones 3 and below, our main concern is the summer. Our main concern is that outside heat and humidity coming in. Once we're in climate zone 5 and up, our main concern is the winter. We really need to prioritize how is it going to dry through diffusion towards the exterior. In climate zone 4, we're kind of even. We want to be able to dry in both directions. And so we really never want to have 2 vapor barriers. One could make sense on the exterior side of a below grade assembly, our damp proofing or our subslab vapor barrier. But we really don't want to use poly membrane on the interior side of our walls, even in our more northern climates. And we really, really don't want to have 2 vapor barriers. So the common one that we're seeing mainly in Canada is the poly membrane on the interior with foil or other types of foam on the exterior. Some type of foam sheathing, whether that's an EPS or XPS or polyiso that's foil-faced. So both of these materials are vapor retarders or barriers, and now we're trapping all the moisture in between them. That can be very risky. I very commonly see this in America in our roofs. Oftentimes projects are doing a closed cell spray foam or pretty thick layer of open cell that might be a vapor retarder or a barrier. The closed cell is a vapor barrier. And then they're topping the roof sheathing with like a grace ice and water shield or other types of bituminous membranes that are truly vapor closed, or a TPO or EPDM for like a flat roof or a low slope roof that's vapor closed. So that top membrane is vapor closed, the spray foam on the underside is vapor closed. Now we're trapping all the moisture in between. And that's how we cause the sheathing to rot. The spray foam companies will say, well, you're vapor closed on both sides, so no moisture can enter. That is theoretically true, and that's what the modeling will show. But these materials start off wet. Wood is quite wet. So it would have to be bone dry. And the other thing is that wood moves based on its moisture content and expands and contracts. So as that wood framing swells in the summer and then shrinks a little bit in the winter, the foam can't move along with it. And now we get these voids and cracks where that foam is meeting the wood, and the foam can trap that moisture and be very problematic. Or where that void is all the way through, and now our warm interior air is moving through and condensing on that cold surface still. So we shedded the water, that's the main thing. We air sealed ideally on both sides of the insulation, complete and continuously. We thought about how it's going to dry through diffusion. For climate zones 3 and below, that means an exterior class 3 vapor retarder. And for climate zones 4 and up, we want to prioritize that vapor variable membrane, the Intello membrane inboard of the insulation. And now we're looking at the thermal control, the R value. This is going to be very different depending on your climate zone. So just like choosing the proper sleeping bag, we're adjusting what level of R value of thermal control we're having based on our climate zone. So in warmer climates, we tend to need a lot less. In more cold climates and more northern climates, we need a thicker blanket. We need thicker insulation. There are vapor permeable types of insulation. Big fan of exterior mineral wool, whether that's from rock wool, most likely. And then there's an exterior wood fiber board, Dutex from 475 or Timber HP, which is based out in Maine. But these are vapor permeable exterior rigid board insulation. So we can still have that continuous exterior insulation that's a board, but use a vapor permeable, more natural type of insulation. We can do a thick layer of blown in insulation, whether that's a TJI or a Larson truss approach. So on the left, we're showing a wood joist outrigger from that sheathing. And then we cover it with a Solitex Mento Plus membrane, which is an airtight, watertight vapor open membrane that also includes a netting to support dense packed cellulose. So that way they can have a big thick blanket of a fibrous blown in insulation outboard of their sheathing. Or for a retrofit, it's oftentimes called a Larson truss or a chainsaw retrofit because they're lopping off the rafter tails. But that's what we're showing on the right here. So they installed the Intello X membrane, their interior air barrier that is inboard of the insulation over the old existing sheathing. And then they did these outriggers built on site, and then that same Mento Plus membrane to then dense pack a thick layer of fibrous insulation, typically cellulose, but there's a wide variety of blown-in types of insulation you can use. So all vapor open exterior insulation. We do really want to be avoiding installing exterior vapor barriers. Here we're showing foil-faced polyiso. The foil is truly vapor closed, and most thicknesses of foam boards tend to be vapor retarders. XPS is much more of a vapor retarder than polyiso. EPS is kind of in between. It depends on which density of that material you're looking at. But folks are doing this to warm that sheathing layer. They're doing a dew point analysis oftentimes. But because that foam is vapor closed or the foil facing on it, they're still trapping the moisture against the sheathing, even though they're warming that sheathing. So here's 4 different projects in Minneapolis. And the bluer lines were covered in 1 or 4 inches of XPS, extruded polystyrene, while the red and orange line did not have exterior insulation. And so when we're looking at the relative humidity on the interior side of the sheathing, we can see that the bluer lines that were covered in exterior foam are well above 80% RH, i.e. our risk threshold for mold growth. So they are increasing the risk and making things worse by covering their assembly in foam. And in the darker blue line, you can see it's actually 100% RH, i.e. true condensation. And you can see this is happening during the winter months, fairly long winter. It's in Minneapolis, but that is when this assembly is trying to dry outwards. It cannot because this foam is a vapor retarder is trapping that moisture. So as we're insulating our projects, we really still need to be drying through diffusion. And we don't really ever want to have these vapor barriers on above grade walls, especially in our northern climates. I could see, again, having like that class 3 vapor retarder in our more warm, humid climates. But we really don't want to be installing, a true vapor barrier outboard of outboard of our sheathing. So we don't want this foil facing polyiso. We don't want to be using XPS. Maybe a thin layer of a low density EPS in like climate zone 1 or 2 could make sense. You might be at about a class 3 vapor retarder with that, but you would need to check the specs. Again, just kind of speaking more to foam, spray foam is not a good air barrier. The material itself is airtight, but it's installed discontinuously. So you'll have air leaks at each stud. And again, the studs are going to expand and contract based on that moisture content. So it's not necessarily that this foam is shrinking off of these floor joists that we're seeing, but the floor joists could just be swelling in the summer because of the high moisture content and then changing its shape a little bit in the winter. As it dries, it shrinks a little bit. And that's how we get these voids and cracks. There could be an off spray mix that could create voids and cracks as well. But here we're more looking at the movement of the framing members. So even once installed perfectly, you should not rely on it as an air barrier. After a few seasonal changes, it won't be a reliable air barrier. And then there are cases of the foam boards shrinking. So this is an article from Fine Home Building about Joe Stiebrick's home, where they used EPS, exterior expanded polystyrene boards that shrunk during the winter. So they allowed significant thermal bridging because the boards shrunk in the colder weather. From an environmental standpoint, and it's really the worst of the worst materials, we want to be using more plant-based materials. The foams tend to have very high embodied carbon or high global warming potential. We want to be building with plants or natural types of material that are sequestering carbon when they're alive, and then they store that carbon within the material. So we can actually have a carbon negative building, which is really great. A lot of the blowing agents used in the spray foams are incredibly toxic. Phosgene is a common blowing agent. It was a chemical weapon in World War I. So let's keep these chemicals and similar materials that would be off-gassing outside of our occupied space. We're breathing in the air around us, so let's not put a bunch of toxic things around us or things that would off-gas. And foam itself is a flame accelerant. So if the mix is off during the spray, it could erupt into flames. But oftentimes the more concern is like an exterior rigid foam and some embers and sparks hit it and can create that foam to propagate flame. So we're now having wildfire seasons for most of America, unfortunately, and Canada. And so we really want to be addressing this and be using higher density materials that are flame retardants or won't propagate that flame. So like wood fiber, it's made out of wood, but it's a high density wood, and there's not enough air that moves through it to propagate the flame. So it chars instead of burns. Similar thing with like straw bale construction. Yeah. So we really want to shed all the water. That's the number one thing. We want to make it airtight, ideally on both sides of the insulation. We're then maybe changing our vapor control based on which climate. For climate zones 1 through 3 and A particular and humid climates in particular, we want to be an exterior class 3 vapor retarder, i.e. between 1 and 10 perms. That would be the Solitex Mento membrane over OSB. We're pairing the high permeability membrane with the lower perm sheathing, or it could be the Adhero membrane over plywood. And then for climate zones 4 and up, we're relying on the Intello membrane on the interior, the humidity dependent vapor retarder that's changing its vapor permeability. And then for R value, it'll be the right amount based on your climate. You can refer to energy code for your region for what to be hitting for that. Or you could be basing it on like a FIAS prescriptive standard or things like that, or ultimately maybe running a WFI hydrothermal analysis on it. So appropriate size for your R value. So again, this is all coming back to which climate zone you're in and how we're kind of adjusting things. And we see that the more southern climates are warmer, i.e. lower in numbers. The more northern climates are colder, i.e. higher numbers. And then C being marine, where we're having significantly more precipitation in the winter than the summers, versus the dry region, which has not very much precipitation throughout the year, or a moist or humid region that tends to have a lot more precipitation. I'm now going to be running through this wall assembly where we have the exterior side on the left and the interior on the right. From the exterior coming in, we have our siding, our rain screen, our exterior insulation as vapor open. We have our house wrap, our sheathing, then our cavity insulation, whether that's a bat or a blown in, then our interior air barrier in red here. This could be the Intello membrane, the Intello Plus or the Intello X. And here we're showing a service cavity, a little chase for you to run your electrical components inboard of that Intello membrane so you don't have to air seal all around it. But it also gives you the opportunity to include a bat additional R value in here, and then our drywall. So kind of talking through how this assembly would be changing. In our hot, humid climates and climate zones like 1A, 2A, we really do want to prioritize this exterior air barrier, and we want to make this a class 3 vapor retarder. So most of our membranes tend to be quite vapor permeable, and we're sometimes relying on the sheathing for that lower vapor permeability. So OSB has a lower vapor permeability than plywood, but in general, I like how plywood responds to moisture if it is getting humid around it than OSB. The OSB, it just has more glue and can't quite flex or move, but neither of which you want to get all that wet. But in a very humid climate, a very warm climate, a very hot climate, I would probably be steering projects towards having the Adhero 3000 membrane over plywood, excuse me, Adhero over plywood, or Mento over OSB. If you're having exterior insulation, it's probably quite thin. You probably don't need very much of it. And an interior air barrier is helpful, but maybe not as needed in climate zone 1 or 2. Becomes more and more helpful as we're moving more north. So for climate zone 3, there's not a big difference. I would say you're maybe thickening this insulation level a bit more. I would still stick with the class 3 vapor retarder on the exterior for the more humid climate. For dry climates or marine climates, I am comfortable with that exterior being quite vapor open or vapor permeable. So you could be using the Solitex Mento membrane over plywood or the Adhero 1000 membrane, which has a higher permeability than the Adhero 3000. So that'd be more like in your climate zones 3 and marine. For once we're getting into climate zone 4, we're having more robust R value, we're having more real winters. I would now be really prioritizing this interior air barrier. For our humid climate, in terms of climate zone 4A, I still really want a strong exterior air barrier as well. We really do need to air seal both sides of that. For dry, for B, that exterior, it's very helpful for it to be airtight, but I really want to be prioritizing that interior air barrier. Our sheathing can be getting quite cold during those winters, and I want to keep my warm air off of that sheathing surface. So now we're maybe switching to 2 inches of exterior insulation. We're probably using a 2x6 cavity that we're filling with a mineral wool bat or unfaced fiberglass bat or a blown in cellulose, and really prioritizing a good Intello membrane. And then for climate zones 5 and up, again, we're really prioritizing this Intello membrane and we're just making all of our insulation layers thicker. We're trying to increase the vapor permeability on the exterior. Climate zone 6 is oftentimes where I'm seeing projects do sheathingless assemblies, where they're using diagonal strapping or lead-in bracing instead of a plywood or OSB sheathing, because they don't want the vapor retarding qualities of that plywood or OSB. Maybe they're switching to a masonry sheathing, like a dense glass element that has a higher vapor permeability. Some other climates might be doing that for their fire ratings. But once we're in these more northern climates, these cool or cold climates, our vapor drives prior mainly from the interior going out. So that Intello membrane becomes very key, and we want to have a very high vapor permeability on the exterior, such as the Solitex Mento membrane, whether that's over plywood or if they're going sheathingless, it would be the Mento Plus that would have the netting built in. So we're slightly tweaking things based on climate zone. We're maybe changing that exterior vapor permeability some. We're changing our levels of R value, but in general, we're still shedding the water as number one. We are still air sealing projects regardless of climate zone. We're adjusting our vapor control a little bit, and we're adjusting our R value. But there is still that order priority. I do want the assembly to dry through diffusion more than I want the assembly to be super insulated. So those projects that are really getting tunnel vision on the R value and that are spray foaming and or running exterior rigid foam, they're having a really high R value, but they're losing the importance of that vapor control or that air sealing. And it could be trapping moisture. And even though it's a super insulated wall, that trapped moisture is really, really dangerous. And even more so because it's super insulated. So that is increasing the risk by super insulating. We need to really care about how it's drying through diffusion. And in these more northern climates, we really don't want to have exterior vapor retarders. We're really mainly drying outwards most of the year. So this is the 475 website. Check out our ebooks and our blog. We have different sales team members across the US or Canada. So these ebooks are a good starting point, but please reach out to your local 475 sales rep. They're happy to talk through these types of principles of the building science and help select the proper materials for your specific climate zone, but also your specific project. So we're oftentimes bouncing assembly details back and forth with designers, helping talk through different options, helping select the proper water resistant barrier, helping select the proper interior air barrier. And then we're doing a similar conversation with the builders, oftentimes highlighting sequencing concerns. Let's make sure to place this interior air barrier before we run the top plates for our partition walls, for example. Or let's remember to cover the rim joist with a piece of tape for our air barrier transition around a floor system. We can also help with the contractors with their estimates and pricing, and then talking through things on site or helping with quality control. So please reach out to your local 475 rep. And thanks everyone for joining.